always manage to organize very stimulating symposium or conferences, and with a lot of good food, etc. So thanks for that. So let me very quickly go through this talk. Let me make sure nope, this one. Okay. So I acknowledge the support from NSF for the work that I will be presenting. Okay. All right, I will get hold of this. All right, so the previous speaker has already introduced to you the idea of granular system. So this talk will focus on how we can exploit granularity of matter for doing something more. Okay, right. So we know that all matter is granular, and this was known by our ancients a long time ago. I usually like to present this sutra from Nyaya Sutra of Gautam, which was dated in 1st millennium BCE, which says that matter appears as whole or continuous, like a pile of hair may appear to people with impaired vision, right? And then Gautam goes on. It takes about another 10 sutra. Now sutras are they are very compact statements of logic, and he goes on to argue that matter has to be discrete, right? Okay. So anyway, this is the inspiration for the work, right? Okay. Now I think in our own lives we can experience this. I show you a picture of a limestone, okay? And you see limestones here a lot if you walk around, and if you look by your bare eyes, it looks merely more or less continuous. If you see at higher resolution, you may see some texture, or some limestones you can see texture. But if you go within those textures at even higher resolution, you can see a variety of granular systems, right? Okay. And these granular systems can be defined at different scales, right? Okay. So different scales and different ways that the grains are interacting with each other. Right? Of course, you can go to the beach where the interaction is mainly because of compression action or shearing action between the grains. If you pull them apart, they are not interacting. But you have a range of materials that can be generated from this basic idea. Right? Okay. So you have seen in the previous talk that material granularity can give rise to a variety of phenomena, right? Some of which Luca has described very vividly, right? Okay. I present to you two examples here of sandstones, where I think the question of localization came up, where you observe that localization is never a infinitesimally thin zone. Right? So the fracture in all systems has some finite length, finite thickness. Okay? And these are shown very clearly in these kind of sandstone systems. Okay? In fact, in mineralized tissues, right, which are composed of apatitic crystals are of the order of tens of nanometers, right? Usually around 10 to 20 nanometers. Embedded within a matrix of collagen. The fracture, when we fracture our bones, I don't know how many people have fractured their bone here, but if you fracture your bone, the precursor, before the fracture, before the break completely develops, it has been observed that you have these kind of dilatational bands which then coalesce, they become the precursor to the localization of strain. And this is happening because of granularity of the material, right? Okay. So the key point is that the material granularity is a cause of a number of phenomena, And what we would like to do is to exploit that to see if we can come up with some other material systems which are maybe hidden. They are already available to us, but not so obviously, right? Okay, so exploit granular motif for metamaterials. All right. So we ask, so before I go further, I want to define what we mean by grains and granular material as they relate to the meta questions that we ask here, right? So grain to me is a geometrically bulky object with clearly recognizable or demarkable boundary. Okay? Now in some cases, these boundaries may be welded together or glued together to form interfaces. Granular material or particulate material would then be a material system composed of nearly rigid elements or grains, such that elastic strain energy is stored or energy is dissipated in the deformable mechanisms that can be represented through interconnections or interfaces between these rigid elements, right? Okay. So this would be a strict definition of a granular material from my viewpoint. Okay. But you can extend it further by saying that one can represent or such a view can be representative of materials which have this kind of granular microstructure in which the deformation of interacting grain pairs can be effectively described in terms of relative motions of grain centroids regardless of the location where the actual deformation occurs, right? Okay, so in other words, you can view this material as made up of points which are interacting through deformable mechanisms, like in peridynamics and like what Luca has presented. Okay. All right. Okay, so when we try to construct explanations for the deformation behavior of such systems, in other words, we seek the explanations for meta questions, right? The explainants or the methods we develop should have certain characteristic in my viewpoint, and I borrow this idea from Hempel and Oppenheim's classic paper, okay, where they have argued that an adequate theory is one in which you can make a prediction, okay, before you make an observation, right? Okay, so a theory is not one which is explaining observed phenomena, but an adequate theory, a theory more strong, is one which predicts a certain phenomena, and then you observe that phenomena, right? Okay, so I'm seeking such an explanation, right? So this is the explainant I'm seeking, and we will see what kind of explanations or predictions we can come up with, which we can then try to verify, right? So we ask the question, what is this kind of theory which is most appropriate for describing behavior of these kind of granular materials at scales where you have very large number of such materials, right? Such grains, right? While incorporating the effect of the grain scale. Okay. So the answer, I think, should be clear, right? When we have very large number of grains, if I try to follow every grain, I'm causing a lot of expense, not only to the computer, to my own brain, and to all the paraphernalia I have to develop in order to interpret the result, right? Okay. So it has to be a continuum theory, but such a continuum theory which is informed by the grain scale, right? And you have already seen an example, so I think the mystery is not quite there, but you see where we are coming from, right? Okay, so the approach we follow is what we've been calling granular micromechanics approach, okay? And this granular micromechanics approach proceeds from the Piola's ansatz, which is an identification of the micro-macro scale kinematics. Right? And then you can build from that point onward. So we adopt that ansatz, and we begin by identification of grain or micro scale motions in terms of the continuum or macro scale deformation measures. Okay? And then we can express the continuum energy density in terms of the volume average of the intergranular deformation energies. And with this, we can derive the constitutive relations, etc., following the variational approach. Right? Okay. All right. Okay. So what I will do in the remainder of this talk is to show you an example of the application of this ansatz. Right. Okay. All right. So one way we can do this micro-macro identification is through what I'm showing on the view graph here. Okay. So at the macro scale, all right, at the scale where the grains are latent, the grains are not visible to you. Okay. At that scale, you have the usual displacement kinematic variable. However, if you zoom into the material point and make these grains visible, then one can describe this additional motion of the grains. These grains are not following the macro scale exactly, and we have a lot of evidence of that there is not a problem. So you can describe that additional motion through a micro scale displacement, which is a function of this micro scale coordinate system. Right? Okay. All right, so in this way, you can write the displacement of every grain within the system as the sum of the macro scale, which I've shown here as phi bar now, and the micro scale, which is an expansion, a series expansion, where the interpretation of these psi's can be made easily. Dimensionally they are gradients, right? And that's how you can interpret them, right? So they can be called micro strain or micro gradients, right? Okay. All right. So this is the idea of micro-macro identification for the kinematics, right? Now I will specialize this for a one-dimensional case, okay, and show you some results. So these are beams with granular motif. Okay. All right. So in a one-dimensional case, you have these two displacements of grains, which are then decomposed, as we have shown in the previous view graph, in terms of the macro scale displacement and these micro scale measures, which are gradients. So this is the first gradient, this is the second gradient at the micro scale. These psi's are functions of the macro scale coordinates. Phi bar is also a function of macro scale coordinates. So this is what the micro-macro identification is. Okay. All right, then we introduce these relative measures, right? If all of these relative measures are vanishing, in that case you reduce the theory to the classical continuum theory of Cauchy type. Okay. Right. In case these relative measures are not vanishing, then you have some enriched continuum model. Right. And in this particular development, I have assumed that this gamma 1,1 is vanishing. Then let's see, we said, okay, we assume that this guy is vanishing. So gamma 1,1,1 is then the gradient of psi 1,1. So we make a choice of certain relative measures as vanishing, and we reduce the number of kinematic variables down to a few. And what do we have? We have the macro scale displacement along the axis of this beam, macro scale displacement transverse to the axis of the beam, right? Then of course you have the gradients of the macro scale displacements, and you have some micro scale strain, right? And you can write your macro scale deformation energy density in terms of those kinematic variables, right? Okay. Now, if we take this kinematic identification and calculate the relative displacement of the grains within this beam, those can be written in this way, right? And expressed, of course, in terms of the macro scale kinematic measures we have introduced, right? Okay. And in this way, right, we can make an identification, or we can find what is the movement or relative displacement along the centroid of the grain, right? And say in terms of this gradient phi bar 1,1, right? The transverse or the shear displacement between two grains, okay, and the rotational relative rotational displacements between two grains, okay. All right. So this just falls from simply considering the relative movement in one dimension here between the two grains, right? Okay. So at the two grain or a grain pairs level, then the micro scale or deformation energy can be written in terms of these three relative motions. Of course, here we have also considered all the coupling terms, right? Okay. And this is the same thing we did at the macro scale. So macro scale also we have these coupling terms included in our strain energy density definition. Okay. All right. So following this Piola-Ansatz, we can make a identification between the macro scale and the volume average. In this case, it's one dimensional. So the line average of all the grain pairs within the system. Right? Okay. And you can identify then the macro scale stiffness coefficients in terms of the micro scale stiffness coefficients. Okay. All right. Of course, you can also find the equation of motion for this model, including the boundary condition. Right. Now, what is noteworthy is that if we ignore or if we remove all these coupling terms, then you will end up with a beam model, which is what is described as Timoshenko beam model, and I show it here. So there are two kinematic variables that will survive. It is the transverse displacement and its gradient and the rotation, right? Okay, and its gradient. Right? Okay. Of course, if we want to identify this Timoshenko beam in terms of isotropic elasticity, you have some restriction on the ratios of this rotational stiffness and the shear stiffness, right? Okay. Right. This is classic. However, here there is more generality. So you can have things which are not restricted by this ratio, and of course you can have these coupling terms. Okay. All right. So what we find is that if these coupling terms are non-zero, then you get some results which are not standard. Okay. All right. So we take this model and we calculate a very simple case where we take the beam and simply extend the beam. Right. So if you extend the beam, the expectation is that the beam will deform without any bending or transverse deflection. Right. This beam, if we include these coupling terms, okay, these are just non-dimensional forms of the coupling term, okay, then they show that under extension, simple extension, you have some transverse deflection and you have bending of the beam. Okay. So the question is, can we realize such a beam, right? Okay. Because the macro model, this continuum model of derived through this effort, is showing us this type of non-standard behavior, right? Okay. The clue to finding such a beam is in the micro-macro identification, right? And this micro-macro identification is telling us that the macro scale stiffnesses are related to grain pair stiffnesses, right? Okay. Particularly these coupling terms are related to what would couple the normal to shear deflection at the grain pair scale, right? So if I can design a grain pair in which if I make a stretch, there is some shear, right? Or if I make a stretch, there is some rotation, then I can find a beam in which such a behavior will be seen, right? Okay, so it's not so difficult to design such a grain pair. We can simply put these three ligaments or three little beams, okay, between two grains, and the grain pair now has a fully coupled system of stiffnesses. So for example, if you stretch this this grain pair, you will have some resistance in the shear direction, you will have some reaction to rotation, etc., right? Okay. So with this kind of grain pair, we can now create beams and make measurements, and this is what we have done. So I think what I will do is maybe not spend too much time on describing everything, but show you what the results are, right? Okay, so we do a digital image correlation. Here I want to make a remark. If we do a digital image correlation without the pre-knowledge of the microstructure, okay? Right. Suppose this microstructure is at the scale which we are not typically measuring, right? Okay. So if I do a digital image correlation, assuming that this is a regular beam, right? This case, what we will observe from digital image correlation is given by what you see in D and F. So D is showing the transverse deflection of the beam as the beam is being pulled. F is showing the axial deflection, right? Okay. What I want to remark is that if you look at the magnitude of the transverse displacements, they are order of magnitude smaller, okay? Right. So a typical reaction could be that these are very small, 1/10 of the imposed displacement, therefore could be negligible. However, I have to caution, they are small but significant, right? Because there is a significant amount of energy, of course, stored in the action, and the consequences of this mechanism is quite remarkable, as we will see. All right. Okay, so that's the point for this view graph. Of course, when we make the measurement for this beam, we find exactly what we have predicted, right? You stretch the beam, you have transverse displacement, and you have bending of the beam, okay? All right. And one can make a prediction without making any measurement, and because in this case we can characterize the system very well. We know exactly the size of every grain, the size of every beam. We can pre-calculate the stiffnesses and make the predictions. And you see, by and large, the agreement is quite good. Of course, there are some areas of disagreement, which just says to me that the theory is missing something. Okay, all right. Okay, so what are the consequences? Well, the consequences you can see. So consequences of this transverse, that order of magnitude smaller transverse displacement, you can see when you produce a similar grain pair in a two-dimensional structure. Okay, so here is a 2D structure which has a square symmetry or orthotropic symmetry. Okay. And in this case, okay, without going through, so we go through the same kind of identification that I have described before. The macro scale strain energy is given through this kind of model where we include additional macro scale kinematic variables, which are the rotation, like Coursera rotation, and of course there is the coupling between rotation and the stretch, right? Okay. And we make the same kind of identification. We can find that the coupling terms, how they may be related to the macro scale, etc. So the local coupling terms, okay. All right, so we make the same, of course, fabricate this kind of system and do the digital image correlation, okay. All right, so what is surprising? Of course, you see the under compression. So these are results under compression predicted by the continuum model, right? Okay. And the continuum model is predicting that, of course, these fields, so you have the axial displacement, right, is not linear. There is transverse deflection, which is here, which shows a negative Poisson's effect, okay? And you have, of course, a rotation field, and the energy density is not symmetric in this system, right? Okay. This here is then the comparison between the predictions and experiments of the grain scale. So these are all grain motions which are predicted by the continuum theory. And okay, so this is, I'm sorry, let me see. Yeah, so the top panel is all predicted, measured from the DIC, and then the bottom panel is predicted by the continuum theory, right? Okay. Okay. So the key consequence, of course, is you can see there is negative Poisson's effect. There is chirality. These are handed systems. You can see if I make a mirror transformation, or in order okay, you need mirror transformation in order to match the fields, right? Okay. All right. So the conclusion is that we can, with correctly formulated theory, we can find such systems, or we can answer questions like, can we link micro macro scales in a way that we do something at the micro scale in order to obtain a desired emergent behavior at the macro scale, right? And can we verify these through other independent methods and experiments, right? So what I've shown to you is through this micro macro correlation, which we call granular micromechanics, it is indeed possible to do this thing, and these links point towards a goal for rational design of material microstructure. Right? So I will stop here. I acknowledge the work of many people which have gone into the over several years, several decades of thinking about these kind of materials. I'm happy to answer any questions.